Hello and good evening. Can you just tell me whether you can hear me, please? Brilliant, yes. So a little bit of a delay, but we'll live with it. So Maria, I think that's how I pronounce your name. Hope I did that right. So all exam boards have hypothesis testing in. So the A-level maths exam boards are aligned now, so this is for all of them. So it's useful no matter what exam board you're doing. So we'll get straight into it. So last week we did the binomial distribution, which is absolutely imperative in understanding what we're about to do tonight, which is binomial hypothesis testing. And binomial hypothesis testing is, and I'll write this down, it's a method for testing for a change in the population parameter P in a binomial distribution. And by parameter, the binomial distribution has two parameters, two things that we need to define what the distribution is. It has n, the number of trials, and p, the probability of success. So what we're going to do now, we're going to go through what a binomial hypothesis test actually does. So I like to think about it as a way of testing whether somebody's lying to you or likely lying to you. So we all know somebody who tells lies. Meet them all the time. And some of the lies are so absolutely ludicrous that you're willing to call them out on it straight away and say, nah, you're not telling the truth. However, some of the lies could be a little bit more subtle. Some of them could be, well, almost believable. So in such circumstances where the lies are, almost believable, maybe pushing the truth a little bit, we're maybe not so confident on calling someone out on lying. And that's what binomial hypothesis testing does. It gives us a way of calling out with a certain degree of certainty whether somebody is lying or not. So let's have a look at this particular one here. So dice used in playing a board game is suspected of not giving the number 6 often enough. So we think that the dice is dishonest. During a particular game, it was rolled 12 times and only one 6 appeared. Does this represent significant evidence at the 5% level of significance that the probability of a 6 on this dice is less than 1/6? So there's a lot to digest here, and we're going to go through it step by step. So first of all, step 1. So we're going to test objectively whether this dice throws enough 6s out. We suspect it doesn't. So step 1. Define in words the parameter P we are testing and state the null and alternate hypotheses. And this is a particular branch where we've just got to do loads and loads and loads of examples until you actually get it. So it's a very difficult topic to introduce. So bear with it. After about the third or fourth example, the mist will start to clear. So what we're testing, basically, is whether P is a sixth, and we suspect it to be less than a sixth. So define P in words. So P equals the probability that the dice rolls a 6. And state the null and alternate hypotheses. So the null hypothesis is us giving it the benefit of the doubt. All is good with the world. So H0 colon, that says the null hypothesis is, don't write H0 equals, write H0 colon. You must write it exactly like this in order to get the marks in an exam. So our null hypothesis for the dice is that the probability is indeed 1/6. So some wrong ways of writing this. H0 equals a sixth with no marks. H0 equals P equals a sixth, no marks. Has to be H0 colon P equals 1/6. So this is the industry accepted standard. And what that says is our default position. I'll make that look more like the word default. Our default position is that the dice is fair, i.e. the probability of rolling a 6 is 1/6. But then suspicion kicks in. We suspect that the dice has a probability of a 6 less than a sixth. So this is our alternate hypothesis. And what we're trying to do here, we suspect that this is the case. We're trying to gather enough evidence to a certain level of certainty to suggest that this is wrong. So it's much like a court case, innocent until proven guilty. We assume that this is the case, that the dice is indeed fair, but we're trying to gather enough evidence to show people that it's unfair. As I said, just like court, innocent until proven guilty. So overall, we've just gained 2 marks by writing this out. Possibly 3, depending on what exam board you're on. So I haven't done any maths yet, and already we're getting marks for a question like this. Right, step 2. Use the observed data to perform the test at the given significance level. Now, I haven't even told you yet what a significance level is, so we'll have a look at that now. So, when your friend tells you a lie, as I say, picture this friend in your head who says a lot of untruthful things. There's a certain level you get to when you think to yourself, I'm not putting up with these lies anymore. He said something so ridiculous, or she, so ridiculous that you're going to have to call them out on the lie. And that's what the significance level is. basically, it's the level of lie we're willing to put up with. So if somebody here says something less than 5% likely, that means you're 95% certain that they're lying. So that seems a fair time to call them out. So we've decided, arbitrarily, randomly, that we're only willing to accept his lies until they become less than 5% likely. We want to be 95% certain that he's lying before we call them out. So if what they say is less than 5% likely, we're going to call them out. And the way I'm going to do that, I'm going to think of the likelihood as being contained within this box here. This is a box full of probability. So that box overall contains 1. All probability is stored in this box. And we're calling out lies that are less than 5% likely. So anything that lies in the bottom 5% of this box, we're going to classify as being a lie. So we're going to reject what our friend says if what they're saying is less than 5% likely, i.e. if it lies at the bottom end of this probability box. And this is called the rejection region. And the top 95% is called the acceptance region. So remember, if what they're saying is so unlikely that it lies in this bottom 5% of probability, that it's less than 5% likely, we're going to reject what they say. We're going to call them out on lying. So we're saying the probability of rolling a dice is less than a sixth. So we're going to do an experiment to try and prove it. So we do the experiment. We roll the dice 12 times. And we see there's only 1 6 that appears. So if we roll the dice 12 times, we know from last week that's a binomial distribution. 12. We have 12 goes at it. And the probability of success, if all is good with the world, if indeed this guy here is telling the truth, then the probability is a sixth. And we have no reason to disbelieve it yet because we haven't done the experiment. So we'll roll the dice 12 times and only 1 6 appears. Type in the chat how many would you actually expect. If we roll the dice 12 times, how many would we actually expect? Roll the dice 12 times, probability of a sixth. How many sixes would we expect to happen? Christine, I agree, 2. We'd expect a 6 to come up 1/6 of the time. So 2 of them. Okay. And we actually have only observed 1. So it suggests that the probability is indeed a little bit less. But the question is, does that tell us we're 95% certain that it's less? Was this less than 5% likely to have happened? Was this lie, or alleged lie, less than 5% likely to have happened? If it was, we're going to call them out on lying. If it wasn't, we're going to grate our teeth and just get on with life. Let them off with it. We're not 95% certain. The lie wasn't less than 5% likely, so we haven't got enough evidence to call them out on it. So what I'm going to do here is see how much probability lies to the left of what we observed. How much probability lies to the left of what we observed? We observed 1. Because what we're trying to do, we're trying to place the observation 1 in this diagram to see whether it's in the rejection region or the acceptance region. So I'll show you what I mean by that in a second. And as I say, these examples are confusing at first. So menu, and we'll go into the binomial distribution mode. Binomial cumulative, because we're doing less than or equal to. Variable. It's the probability that x is less than or equal to 1, where we had 12 trials, and the probability was 1/6. And the probability that x is less than or equal to 1 is 0.3813. So basically, our observation, 1, there's 38% of probability that's to the left of it. Less than or equal to 1, 38% of probability to the left of it. So I'm going to place it on this diagram. It's certainly not going to be there because that's the 5% mark. If that answer there was 5%, 1 would go exactly there. It's going to go somewhere there. So it's not in this list of lies here that we would use to call somebody out and say that they're lying. In fact, there's far more probability to the left of it. It sits there in the acceptance region. If this was less than 5%, if this was less than 0.05, it would lie in this region. So step 3. Compare probability obtained to the significance level if less, reject what we assume to be true, H0, if more, do not reject, H0. So the amount of probability to the left was 0.3813, 0.3813, which unfortunately is more than our significance level, not less likely. So we're going to have to just keep our gobs shut and assume that they're telling the truth. So we're going to not reject H0. And I'm taking this very slowly because this is quite a difficult concept to get across. Do not reject H0. And then finally the fourth step, always, conclude in context. So insufficient evidence to suggest that the probability, and don't get lazy with conclusions here, must write all this to get the marks, that the probability of rolling a 6 is less than 1/6. And there's loads of marks to be gained here. So 2 marks there at the very top. Using the distributions worth a mark, so write that down. Perform the calculations worth a mark. Comparing to the significance levels worth a mark. Stating reject or do not reject is worth a mark. And then the conclusion's worth a mark. So these are usually 6 or 7 marks. Usually 7 marks. And to be fair, only one of them is actually for maths. And that's for putting something in the calculator. So this is one of the topics that students hate the most. But it's one of the easiest ones to gain marks in. So let's try another. So let's do a question that doesn't have a context for now. Let's just do a pure hypothesis test question. So there it is there. So a single observation, x, is taken from a binomial distribution, and a value of 5 is obtained. So that could be thought of as rolling 5 sixes. Use this observation to test the null hypothesis that the probability was a quarter against the alternate hypothesis that the probability was bigger than a quarter, using the 5% significance level. So there's no context to this, so we can't really say in words what it's representing. Like before it was about rolling 6s on a dice. There's none of that currently. But let's just write the hypotheses out anyway. So we've got the null hypothesis that the probability of winning was 0.25. And this time we suspect the probability of winning is bigger than 0.25. We're assuming this is true, but we're suspecting that this is true. In 10 goes, if the probability of winning was 0.25, how many wins do we think we get normally? We play it 10 times. Probability of winning is a quarter. Non-integer answers in this context are fine, by the way. How many wins do we think we get when we play it 10 times with a probability of a quarter of winning as an estimate? Sophia, good. 2.5, a quarter of 10. A quarter of all goes will be wins, so we'd expect 2.5 wins. Now in reality we can't get half a win, but it's just an estimate. In reality, yeah, Christine, just seen that now, correct, 2.5. In reality we won 5 times, so that's suggesting to me something's up. That's way more than a quarter. So let's draw my little probability box. And notice, before, on this one, we were testing for a decrease. We thought the probability was less than a sixth. So the 5% that we're rejecting was on the bottom, on the less than side. This time here, we're testing for an increase. We think that it's actually bigger. So what we're going to do this time is test on the right-hand side. And when we're testing for a decrease, and we can see we're testing for a decrease because it says there, less than. When we're testing for a decrease, we call this the left-hand tail. This here is the left tail. We're testing for an increase this time. So the top 5%. This is going to be the right tail. So this is the rejection region. And this is the acceptance region. And we're testing, based on the data we've obtained, whether this is telling the truth. To me, currently, it looks to not be telling the truth. I was expecting only a quarter of them to be wins. I was expecting only 2.5 wins. And I can see we've obtained, actually double that, we've obtained 5 wins. That looks a significant difference to me. The question is whether this was less than 5% likely to have happened. If this was less than 5% likely to have happened, we can call this guy out as lying. If not, we're just going to have to accept it. We've set ourselves a tall order and been 95% certain that they're lying, i.e. that their story is less than 5% likely. So this time we're going to test how much probability is to the right of our observation. We're testing for an increase, so we're trying to place our observation, which is 5, somewhere on here. So we want to see whether it's in the rejection region, i.e. if there's less than 5% probability to the right of it, or whether it's in the acceptance region. So I'll put that there for now. We'll come back to that. We'll place that on the diagram once we've tested how much probability is to the right of it. So the probability that this time x is greater than or equal to 5 equals, and looking at what we did last week, 1 minus the probability that x is less than or equal to 4. So let's put that in the calculator. And what I should do as well, I should write down the distribution that I'm testing. So x has a binomial distribution. Number of trials 10, and 0.25 is the probability that we're assuming to be true. Might not be. That's what we're trying to find out. Okay, so x is less than or equal to 4 is the one we're calculating. We have having 10 trials and probability of success. We're assuming initially there's 0.25, giving the benefit of the doubt. So it's 1 minus 0.92187. Like that. Equals. So 1 minus answer equals 0.07813. We were so close to being able to reject that lie, but unfortunately we set ourselves a 5% likelihood target, i.e. we wanted to be 95% certain they were lying, and currently we're only about 93-94% certain that they're lying. Whilst we're still pretty sure they're lying, we set ourselves a tall order of what they said being less likely than 5% to happen, and we haven't got that. The amount of probability to the right is 7%, which pushes it just outside of this rejection region, unfortunately. So remember, to get the marks, compare to the significance level. 0.07813 is actually outside, is bigger than the significance level. Therefore, unfortunately, do not reject H0. I thought we had it there. So again, they're likely to be lying. 94% likely to be lying. Unfortunately, that's just not good enough for us. We set ourselves a 95% target, a 5% significance level. So we're just going to have to move on from it. Let's try another. Again, we'll take this one out of context. So it's all about how certain you are that they're lying, how likely that was to have happened, where we would put it in terms of likelihood on that probability diagram. So, got that there. Have a look at that one, see if you can do the same again. So random variable has distribution x binomial 10p. A single observation of x equals 1 is taken from this distribution. We play the game 10 times, we win once. Test at the 5% significance level. And it doesn't have to be 5%, it just so happens that currently it is 5%. Test at the 5% significance level. The null hypothesis, that p is 0.4. So I'm going to ask you again, if the probability is 0.4 of winning, out of 10 goes, how many wins would you expect to get? Probability of 0.4, how many wins would we expect to get? Yeah, Sophia, yeah, Christine, 4 of them, definitely. 4 tenths, 0.4. So 4 wins. However, we only got 1. Again, this looks promising. We got a quarter of the number of expected wins. I reckon we've got it here. I reckon we're going to be able to say we reject. I won't know until we try, but I think we're going to be able to say reject. So, in this case, we've been given the null hypothesis. We're saying that there's a 0.4 chance of winning, and we're going to give them the benefit of the doubt. We're trying to gather evidence to say they're lying, but we again want to be 95% sure that they're lying. The story they tell has to be less than 5% likely. And sorry if I'm over-egging the pudding here, if I'm over-emphasising the point, but that's the key point with hypothesis testing. And we're suspecting that actually the probability of winning is less than 0.4. So there's our probability box. And we're testing for a decrease now. We're thinking that it's lower than expected, so lower to the left. So any story on this left-hand side, less than 5% likely, is going to be rejected. So let's test now how much probability is to the left of our observation, which was 1. So we're going to try and place 1 somewhere in this diagram. So how much probability is to the left of it? So the probability that x is less than or equal to 1 is equal to, straight in the calculator, so binomial cumulative variable. So x is less than or equal to 1. We had 10 goes and the probability of 0.4. 0.0464. And again, I should really state the distribution that I'm using, which was 10, 0.4. And we've done it. The probability to the left is only 4%, so it's in this rejection region. Only 4% of probability lies to the left of it. So that's where it lies. .0464 is less than our significance level. Therefore, we're going to call them out on lying. Reject H0. If something this unlikely happened, we can't believe this. So let's have a look at it in a bit of an exam context. So I'm going to get a question from my categorized exam questions. And what we're going to do, we're going to show you exactly where all the marks are in these questions. These questions are dead easy to get marks on. It's a routine that you've got to get into. So the question that I'm going to have a look at and we can see when it pops up on the screen that, as I said before, it's 7 marks. So there it is there. So a television company believes that the proportion of households that can receive channel C is 0.35. In a random sample of 14 households, it's found that 2 can receive channel C. Test at the 2.5% significance level. So see, it's not 5% anymore. So this time we want to be 97.5% sure that they're wrong before we call them out on lying. Test at the 2.5% significance level whether there is evidence that the proportion of households that can receive channel C is less than 0.35. So back to our original way to gain marks. The first mark requires us to define in words what P is. So P equals the probability of a household receiving channel C. As I say, don't write too little. If you write too little, then you will lose marks. Our null hypothesis, well, we're going to take for granted what they say. We're going to believe them, give them the benefit of the doubt that 35% of households, proportion of 0.35, actually receive channel C. Can you type in the chat what the alternate hypothesis is? P something, 0.35. You just type the sign in the chat. The sign that goes there. Indeed, it is less than, yes. And it says so there, less than 0.35. So already we've gained 2 marks. Those 3 statements between them are worth 2 marks. Differs slightly from exam board to exam board, but if you write that, you're guaranteeing yourself the marks. Right, so the next bit, what we're going to do, we're going to perform the test. So we find that 14 households are tested and only 2 can receive it. So we're testing for a decrease, so the bottom 5% of probability in this diagram is what we're going to reject. Testing for a decrease. And our observation of 2 is what we're going to try and place in this diagram. So our distribution has 14 trials, and we're going to assume that the probability of success is 0.35. Writing that down and using it is worth a mark. So the amount of probability to the left of it, probability that x is less than or equal to what we observed, 2. So we're going to use this to try and place this 2 here on the diagram. So the probability that x is less than or equal to 2 in a distribution of 14 trials and a probability of success of 0.35. We see that 8% of probability is to the left, 0.0839. So if 8% of probability is to the left of that, it's just outside of our rejection region. A mark for that. So now compare it to the significance level. 0.0839 is bigger than, is outside of our rejection region, which is 0.025. So actually I've made a mistake there. I said 5% here. Now that's a common error, because it usually is 5%, but that's 2.5%. So actually I'm going to have to correct this now. So that should have said 2.5%. There. But I am right in saying that here. Luckily, this diagram isn't worth any marks. I just think it helps understand what's happening. Therefore, it's in the acceptance region. We are not going to reject H0. Insufficient evidence. To suggest that the number of households receiving channel C is less than 0.35, and a better word than number, actually, proportion, is what was used in the question. The proportion of households. So we'll do another. I'm taking this particularly slowly because this is a difficult concept to get your head round. So 55% of pupils in a large school are girls. A member of the student council claims that the probability that a girl rather than a boy becomes head student is greater than 0.55. As evidence for his claim, he says that 6 of the last 8 head students have been girls, using exact binomial distribution to test the claim at the 10% significance level. So if boys and girls were equally likely to become head students, then because 55% of the pupils are girls, we'd expect 55% of all the head students to be girls as well, and 45% to be boys, i.e. in proportion to how many girls and boys there are. So if all is good in the world and girls and boys are equally likely to become head student, then the probability that a girl is head student is 0.55. We suspect it's greater than that. So let's go through all the steps. So first thing, get a mark for defining in words what P is. So P is the probability that a head student is a girl. And if everything is fair, that probability is going to be 0.55. If it's not fair, we're claiming that it's greater than 0.55. 2 marks for that so far. Right, so let's perform the test now. So we're claiming things are greater than. So greater than's to the right. 10% significance level this time. So I'm going to get this right this time. I'm going to write 10% in this box here. So the top 10% of observations will get rejected. So here, our observation, which was 6 out of 8, we're going to try and place that 6 in the diagram to see whether it's inside the rejection region or outside the rejection region. So because we're looking at the right-hand side of the diagram, we want to see the probability that lies to the right of our observation, the probability that x is greater than or equal to 6. So the probability that x is greater than or equal to 6 is 1 minus the probability that x is less than or equal to 5. Let's put that in the calculator. X is less than or equal to 5. And we should state our binomial distribution that we're about to use. X has a binomial distribution. 8 trials. And we're claiming the probability of success is 0.55 if we are to believe this one here. So x is less than or equal to 5 is what we're looking at. The number of trials was 8 and the probability of success was 0.55. So let's check it. 1 minus 0.7799. Just double check that. Yeah, 1 minus 0.7799. Which, if we go into ordinary calculator mode, 1 minus answer equals 0.2201. Let's not forget where the marks are. 2 marks for that, a mark for that, a mark for doing this, and if the probability to the right of it is 22%, this is way outside of the rejection region. Therefore, we're not going to reject it. So 0.2201 is greater than our 10% significance level. That's a mark. Do not reject. H0. That's a mark. Insufficient evidence. To suggest that the proportion of girls becoming head student is greater than 0.55. And that's worth a mark. 7 marks altogether. So I think we've got time for one more. This one here. I'm going to give you a moment. It's unusual that there's 8 marks on this one, but I'm going to give you a moment to have a go at this last one yourself. I'll give you 3-4 minutes, then I'll take over, then we'll finish. Right, so remember to define what it is we're testing. So P equals the proportion of e's in the text. And our null hypothesis is that E appears 90% of the time. Our alternate hypothesis and it says here in the question less than 19%, P is less than 0.19. And hopefully you find this diagram to visualize what's going on helpful. As I say, with no marks, but I just think placing our observation in the diagram helps us decide whether to reject or not reject. And it's 10% significance level, so the bottom 10% of observations will get rejected. Anything with less than 10% probability to the left of it will get rejected. So, 20 letters. So we play this game looking for e's 20 times. And we're assuming that it's correct. 0.19 is actually the proportion of e's. Contains one letter E. We only get one E. So the probability that X is less than or equal to 1, we're testing the bottom end, we're testing for a decrease. So 1. See how much probability is to the left of it. So binomial cumulative. X less than or equal to 1. 20. 0.19 gives a probability of 0.0841. 8% of probability lies to the left of it. So yes, we can reject. It's in the rejection region. 0.0841 is less than 10%. So we are going to reject H0. Sufficient evidence. That's a key word, either insufficient or sufficient. You should use to suggest. We never prove anything with stats, we only suggest. Sufficient evidence to suggest. 4 key words that should be in every conclusion. Or insufficient evidence to suggest that the proportion of e's is less than 0.19. And that's that. So hopefully that's cleared up hypothesis testing a little bit for you. So I hope that was useful. And there's one more of these to go, with the schools being back on 8th of March. So to answer your question, Christine, they both mean exactly the same thing. Critical region and rejection region mean exactly the same thing. So, hope that was useful. And I'll see you for one more of these next week before, thankfully, you'll be back at school or college. So good luck. See you same time next week when I'll finish this topic off.